Pleasure to have today MShavit. It's her first time in the festival. Miko did her PhD at Weizmann Institute. She was a student of Gregory Falkovich, and she's a postdoc and instructor at Courant Institute in NYU. And she's done many interesting things on wave and turbulence interactions, and she's going to tell us today about turbulence of 2D internal gravity waves.
Okay. I'm glad to be here. Thank you for having me. I'm going to tell you about weak turbulence of internal gravity waves. So I know that most of you don't work on weak turbulence, and also you don't, maybe many of you are not familiar with internal gravity waves. So I'm going to keep it very introductory. And at the beginning, I'll show you a lot of movies and measurements. And then at the end, I might get a little bit more technical, but I'll do some of the derivations on the board, and I'll only talk about derivations that I think that are general and fundamental for anisotropic weak turbulence. So if you want, you can think about my talk as a talk about weak turbulence of anisotropic waves, and think about internal gravity waves as a particular case. So this is all joint work with Oliver Buehler and Jalal Shadra from Courant. And I will, if I will have time, I'll show you some results that we obtained with Vincent Labarre. Okay. So internal gravity waves is a particular type of dispersive waves that appear in many geophysical systems, also in the ocean. And there are many types of dispersive waves in geophysical systems, and they can occur on all available scales, so from centimeters to 2,000 of kilometers, but they all owe their existence to some combination of gravity, rotation, and curvature of the Earth. And if you think about mathematically, how can you have waves inside an incompressible fluid? So the way I think about it is that all these waves are created by breakdown of some of the symmetries of the Euler equation, and they enter with a skew-symmetric operator in the equation, and this skew-symmetric operator has eigenvalues which are purely imaginary. In this is the dispersion relation, and they're usually dispersive because there are derivatives there, so they become dispersive. And what is common to all these waves is that they're all strongly anisotropic. So here's a demonstration of all of these forces together, creating what is called internal tides, which is a particular type of internal gravity waves. And I know that rotation is in the wrong direction. And we know that rotation breaks time parity symmetry. So we know that to have it in the right direction, we just need to reverse time. But all I want you to take from this simulation is that the headline suggested by the Daily Mail headline suggested that these waves are weird, but I want to convince you that they are really common and they're in the ocean all the time. Okay, and today I'm going to focus on gravity. At the end, I'll talk a little bit about rotation. And gravity creates internal gravity waves because the ocean is stratified mainly in the vertical direction. So this is a measurement of the ocean density. This is a measurement from the Pacific Ocean. It was taken in the 90s, and what you see here are lines of constant density. And I think I wrote measurement, it's taken all along the Pacific Ocean. And you might be surprised that measurements from the 90s are still relevant, but oh, this is topography. So that part is topography of the ocean surface.
There's an island in the
Yes, that's Hawaii. Okay. And if what you see in the plot is that if you're away from the boundaries and from the surface, so you see that the stratification is mainly in the vertical direction. Oh, and I don't remember if I said that. So measurements from the 90s are still relevant because the ocean is a system that reacts very slowly to changes. So we already know. So in France, I'm allowed to say global warming. So we already know that due to global warming, this picture has changed a little bit, but the stratification in the deep ocean is mainly in the vertical direction. That's still true. And just as we're used to seeing surface waves on the sharp density jump along the surface between the ocean and the air, so internal gravity waves are supported by smooth vertical gradients in density far beneath the ocean surface. And one big difference is that for surface waves, the jump in the density is 100%, and here if you take any two different points in the ocean, you will measure up to 3% difference in density, and these 3% happen to be very meaningful. But you cannot take the analogy to surface gravity waves very far because these waves are very different from surface gravity waves. And I assume that most of you never seen an internal gravity wave before, so I just wanted to show you. So this is a nice experiment that will show you internal gravity waves. So there's a water tank, and this tank is filled with layered fluid. So they layered it with taking layers with different changing amount of salt. And there's this device in the middle of the tank, which is going to vibrate in a specific frequency, and it's going to produce internal gravity wave. And the way you'll see the internal gravity waves is they're going to project light on the tank, and you'll see the gravity wave as a shade. The internal gravity wave is a shade on the wall. So here, I hope you can. I'm not sure you can see it well. Because of do you see? More or less, okay. So with the projector, you don't see it on the wall, but what you see is an X shape of internal gravity waves propagating. So maybe this is better. 1 minute. So we don't see it, I'm sorry, on the projector.
But you see them over there.
Oh, okay, thanks.
Are they standing waves?
No, they're propagating. And there you have a refraction from the boundaries. So you get this pattern of diamonds. Okay. Okay, and they also happen to be an important problem for theoretical modeling because they're considered to be the main trajectory of energy from winds and tide towards mixing in the interior of the ocean. And they currently are not accounted for properly in climate models because the internal gravity mixing is happening on the scales of meters and centimeters, and the climate model resolutions are about 20 kilometers. So now they're just being modeled with some diffusion, and we know that it's not good enough. So this is one motivation to study them theoretically. And usually to describe them analytically, what is used is the Boussinesq approximation of the Euler equation. So this is the Euler equation for an interpretable fluid, where I included also the gravity force in the vertical direction. So V will be my vertical direction along the top, and the density is not constant, so there is a mass conservation equation for a continuity equation for the density. And the Boussinesq approximation is assuming that the density is really linear in the vertical direction, where different an important constant for describing internal gravity waves is the Brunswick-Sala frequency, which you can think about roughly as the slope of the main precipitation. And then we assume that there are deviations from this main profile, which are called either buoyancy, or you can think about them as the vertical displacement in different um, um, when they're multiplied by the right constants. And these equations, so the Boussinesq approximation is assuming that the deviation in density is only important when it's multiplied by gravity, and the rest of the deviations, for example, here, we neglect. So it's only important when it's multiplied by gravity. And then you get the Boussinesq approximation, the Boussinesq equations, and the Boussinesq equations, they conserve energy, which has now a kinetic part and a potential part that depends on the intensity of the deviations from the stratified profile. And if you write these equations on the vertical profile, so you can write it. So I'm going to work today in 2 dimensions, because 2 dimensions has, so I'll show you in a few slides. The 2 dimensions has another conservation law, which I'm going to use to simplify the kinetic equation that I'm going to write. So I'm going to work on a vertical profile. So this is the point in the vertical direction. The next will be one of the horizontal direction, and the 2-dimensional plane captures all the essential parts of internal gravity waves. And okay, and it's not very important to get that for you to remember and how the equations look. You can think about it as the order equation that has also gravity. This is a good approximation to think about the Boussinesq equation. And if you plug in this kind of like that, so of one wave, so you will get that this is an exact solution of this whole nonlinear order equation, and you get it with gravity, and you will get that omega k with this is the dispersion relation where theta k. So now we move the wave numbers going to Fourier space. So theta k is the angle between the horizontal direction and the vertical direction. So if you're used to working with dispersive waves, so you can already see that this is a non-trivial problem already in the linear level. So the dispersion relation is bounded and it's scale invariant. So long and short waves can have the same frequency. And there is also a large set of slow modes. And this is wherever kx is equal to 0. So here, along KC, there are slow modes. And this is going to be a problem from the analytical point of view, or a challenge from the analytical point of view with respect to isotropic dispersive systems that don't have these sets. And if you know a little bit more about, for example, inertial waves or drift waves or Rossby waves, they all have the same property. Okay, so I told you that one wave is an exact solution, but more than 3 waves, they're already not a solution and they interact in triads. And what we expect if we now insert energy at some bounded set of wave modes at long scale, so small case, long scales. So what we expect now to see is that because now waves will interact if we evoke more than 3 waves, so we expect them to so if we excite waves on long scale, so we expect them just to produce more and more waves, and because energy is conserved, we will expect the energy to go to smaller and smaller scales, so large scales. And if these two scales of dissipation and forcing are separated, so because energy is conserved, what it will plot the energy density in wave number K. So if we force it here and we dissipate here, so what we expect is to see some transfer of energy going here. And we know from isotropic systems that if we average over the angle, then we will see here that this cascade, what we call a cascade of energy, is scale invariant and it has some power law. But fundamentally, before we started working on this problem, it was not clear to us that this is what we're going to see for an anisotropic system. Okay, and if we are seeing something like that for an anisotropic system, so one thing that we would like to do is, for example, try to compute this power law from first principles, from the equations. And we would also like, so we know that if this, so for example, for surface waves, which are isotropic, or for isotropic 3D turbulence, we know that the way energy is transferred is isotropically with this power law. And we know for an isotropic system that this is not the picture. So we know that it's usually, there is a strong interaction with slow modes, and it's transferred in a very anisotropic way, so mostly transferred here. So what we would like to do is to have an analytical description of the energy transfer in an anisotropic system, and we would like to understand how is this energy transferred happens in the anisotropic direction. Yes.
I guess so. I got two questions. One is what's the source of the anisotropy? You're just have flat surface, linear gradient, still isotropic in this direction. Is this because of the variations in density?
Exactly. Yes, it's anisotropic in the vertical plane. Yeah, that's why it's that's why 2D is good enough or already challenging enough.
No.
But it's isotropic in this angle, which is called I forgot. Is it called the horizontal angle? Azimuthal angle, yeah. So there is an azimuthal symmetry in the problem.
And my other question is, you're talking about dissipation, but you have the Euler equations.
Right.
So you're imagining that dissipation is coming in somewhere.
Right.
They're not in your equation at the moment.
Right.
Right.
So for internal gravity waves, they actually break before they reach to the viscosity scale. So that's why I don't want to talk about the Navier-Stokes equation.
Got it.
And because I'm going to mainly analyze the kinetic equation, so I'm going to write the kinetic equation and analyze the kinetic equation. So in the kinetic equation, forcing and dissipations you can introduce them through boundary conditions. And because I don't want and these boundary conditions are going to be universal, so they're going to be the same for all the anisotropic systems, and I don't want them to depend on the specific way I force or dissipate the system. Yes.
So, are the slow modes to be thought of as harbingers of flows, which then become an important player in the wave interactions?
I think I didn't understand the first word.
Well, I mean, in other words, the slow mode is just telling us you're going to get flows, as is the case, say, in zonal flows and Rossby wave turbulence.
Yes.
Right. I mean, and then these can become critical players in the wave interactions.
Right.
Okay.
Exactly. So they're going to be very important, and I'm going to include them in my analysis of the kinetic equation in a very specific way. So I don't need to deal with the very hard problem of solving the entire problem. So I'm going to concentrate on the wave part, but I will always keep in mind the shear modes and the quasi-geostrophic mode or the slow modes, because they're going to change the class of solutions that I'm going to look for. Okay. So before we start analyzing the equation, we can ask ourselves, what do we see in the ocean? So in the ocean, there are many measurements of the energy spectrum of internal gravity waves. And what you see in the ocean is mainly weak interaction of waves. So if you plot the spatio-temporal spectrum of energy in the ocean, you see that it's mainly of surface gravity, of internal gravity waves. You see that it's mainly concentrated along the linear dispersion. So it's really most of the energies in the wave modes in the bulk. And in the ocean, it's usually, so the problem is two-dimensional because of the azimuthal symmetry. But in the ocean, it's really hard to measure this variable, and it's easy to measure this variable because what is measure this part of the energy density. So there are just devices, so you can measure along the vertical direction fairly easily. And in order to capture this part of the energy density, so what is measured is, so the energy density in wave number 10 is measured in the ocean in different variables. It's measured in kV, the vertical wave number, and in frequency. And because you see that the frequency is the angular variable, so it's just moving from these variables. So this is still a complete description of the problem. And so here, what you see, I'm going to show you what you see is the measurement. This part of the measurement is in the frequency. And I'm showing you a measurement from the North Atlantic, but it's actually not very important because qualitatively all the measurements look the same in different places in the ocean. And what you always see that you have updated the inertial frequency. So this is usually part of the source of internal gravity waves coming from winds and storms on the surface of the ocean. Then there is a peak in the lunar tide. And then afterwards, there is a broadband spectrum with more or less the same slope. Yes.
This point, say you go from AC to AX, AC was that happened from solution.
What? So this helps. N is the main stratification. Yes, in the deep ocean, it's not a constant, but in the set of depth that I'm going to consider, it's mainly a constant, more or less. But you don't seem to be satisfied, so yeah, okay. All right, and it has been a long-standing theoretical challenge to understand how can you get this broadband spectrum from a monochromatic source 1 minute. So for us, it's clear that this is turbulence, and then it was a long-standing challenge to explain the observed spectrum after the slope after the slope. And okay. And then there are also other small questions that are so the facts are very clear for oceanographers, but they don't have an analytical reason or a fundamental reason why is it true. So for example, one important thing is that I don't know if it's very important, but it's what is measured in the ocean. So the spectrum that is measured in the ocean is separable in these two variables. In all different places, it's always separable in KZ and omega K. And when I asked oceanographers, is it separable because this is the way you measure, or is it fundamentally, there is some fundamental reason for this separability? So they say, no, it's not because we measure, it's really fundamental, but we don't have a fundamental reason for that. Okay, and what we ask ourselves is, can we predict this slope from, or explain that from the equations? And in the 70s, there were two famous oceanographers, Garrett and Mach, which took all these measurements from different places in the ocean and just fitted the data to get these power laws, and they received these two power laws. So this is Garrett Mach. So this was data set. And this is in the two limits when you take rotation to 0. So in the slope, you're far away from the north. So you're here, and in the C variable, you're on length scales, which are small compared to the depth of the ocean. Yes.
Just to understand. So if I somehow know let's say from a simulation, I know the velocity everywhere, then the X direction is periodic. So I Fourier transform around it, and that becomes my omega.
You need also the KZ variable.
Yes, so the KZ
So you
variable.
either measure time, I mean oscillation of waves, and you have the cosine, because this is
the direction, yes.
up to symmetry. So when the cosine is monotonic, you can
Like
move
this.
between time to cosine, to omega. Yes.
Just a quick question. That theoretical, what is the scale at the right end of us right now on the measurements? What's the small scale that are measured?
20 meters.
10 meters.
Let's put it 10 meters before mixing starting to happen.
10 meters. And the depth at which you know where each depth in the ocean is.
So you need to be at least below 500 meters. And you want to be far away from topography. So let's say that we want to be around 1,000 meters beneath the surface.
1/10 meter, right? The KD is 1/10 meter.
Yes, thank you. Yeah. And I want to. Okay, so just to be more honest with you, is that so of course, if you take, so in the 70s, most of the measurements had the same slopes, but if you include also measurements from recent years, so you have some variability in the power laws that you measure in the ocean, in the energy density, but they're all, if you're far away from the natural peak, they all have the mean around the Garrett-Mach spectrum. So the Garrett-Mach spectrum is still considered to be a good and useful description of the density of internal gravity waves in the ocean. So I already told you that that was a long-standing problem, or is a long-standing problem. It has a long history with a lot of great physicists and oceanographers that worked on it. starting from the 60s with Hasselman, and then I told you already about Garrett Monk in the 70s. And there were also attempts of trying to use weak wave turbulence approach or kinetic approach to describe this problem, because it seems like a classical problem for weak wave turbulence. So dispersive waves, if you excite dispersive waves in an infinite domain, so because they move with different group velocities, is if you have an infinite domain, so eventually with time everything disperses and dies. But if you put them in a bounded domain and they have enough, if you want, enough space to interact, but the amplitudes are small, so you can think about them as weakly interacting particles. And then you can think about writing something in the spirit of the Boltzmann equation, a kinetic equation that describes weak interaction of waves. And this is the approach of wave turbulence or of kinetic theory. And it was successful in some cases. It was very successful, like the Schrödinger equation. In some cases, it was more or less successful, like the surface gravity, weak interactions of surface gravity waves. There are some other subtleties that I don't want to get into, but the power law, for example, for the spectrum of weakly interacting surface gravity waves was computed by Powell, which wrote it in an equation and also found a steady solution for the kinetic equation, that a steady solution that corresponds to turbulence, and the power law matches the measurements of surface gravity waves in the ocean and in experiments. And I'll remind you what we would like to understand. So we would like to understand the energy transfer in the anisotropic system, so how it behaves. And if we have a power law, then we would like to also compute this power law from the equations. And okay, and as I told you, there were attempts using weak wave turbulence approach, because it seems like a really good problem for wave turbulence. So the first were already 20 years ago, and they were all really beautiful works, but they didn't, as of now, there was no conclusive prediction for the energy spectrum or for the flux from these attempts. And if you ask yourself, what are the challenges with respect? So one challenge with respect to, for example, isotropic systems. So there is a nice story behind the love of canonical Hamiltonians and canonical variables in weak wave turbulence. So Zaharovi was a student of Tsegdeev, and what my PhD advisor told me is that when he was in his PhD, Tsegdeev told him, okay, go and write all the equations you know in canonical variables, and then we'll see if we can do some theory. So this is what he did, and he did that for surface gravity waves, which is a really important and beautiful part of the analytical description of surface gravity waves. And then he used the canonical structure and wrote a kinetic equation and analyzed that. So in the first attempts of weak wave turbulence with this problem, so there were attempts of trying to find the canonical variables, but the Euler equations or the Boussinesq equation, they are not canonical Hamiltonian. So this is just, it's not a very important part, but for me, it's a nice thing to understand, because then for me, it was once you write the equations, and I'll remind you in a moment what is the canonical and what do I mean by non-canonical Hamiltonian. But once you write the equations in a variational form, so all the symmetries, so the conservation laws are now more clear. So you can write the Euler equation or the Boussinesq equation in a variational form. So phi here, you can think about this as the stream functions, or yeah.
That can be hardly seen.
Oh, sorry.
Better maybe erase that corner and do it.
I'll raise my boat. So I'll remind you from your undergraduate studies that if you have an Hamiltonian system with x and t variables, so the time derivative of this is written like that, when J is your skew symmetric form. And when J is non-degenerate, so when it's invertible, you can bring it to a form that looks like that. And then these are the canonical variables. So then, sorry, there needs to be one. And then just from this form, H is the conserved charge with respect to symmetry in time. And if you have a nonlinear system, so generally usually there are no other exact conservation laws, except maybe for momentum, usually. But if you relax this condition, so J is not invertible, but still skew symmetric and that's enough information, so skew symmetric. So if you have a nonlinear system, when H is quadratic, so to have a nonlinear system, you must pay something in J if you want. And it might be no longer invariant, because it's going to make the system nonlinear. It's going to depend on X and T. And then it might have a non-trivial kernel. So there might be some vectors in its kernel where V is not trivial. And then what you have, so this is called a non-canonical Hamiltonian. So because of this form, H is still the charge with respect to time symmetry. So if we're able to write like that, the Euler equation or the Boussinesq equation, it tells us that the energy that we're used to have, if you want, so now it really deserves the name energy, because you really understand that this is the charge with respect to time symmetry. And then if you have other conservation laws, so one fundamental reason to have them in the Eulerian coordinates, so in the Lagrangian coordinates, you can see the real fundamental reason for having them. But in the Eulerian coordinates, in which we're used to writing the Euler equations, for example, so because J has a non-trivial kernel, you have other invariants, which are called Casimirs, and this is, for example, helicity or entropy in the case of 2D Euler, and this is in the case of 3D Euler. And also in the case of Rossby waves. And in our case, in the 2D Boussinesq, we can write our equations in this form, and because the skew symmetric form J has a non-trivial kernel, so there is another conservation law. It's called the pseudo-momentum and has the same origin as helicity. And it's the correlation between the velocity and the vorticity. Okay, and another challenge in this problem is, I hope I already stressed enough, is that it's anisotropic. So it makes things a little bit more complicated, because now you have more dimensions to care about. So in an anisotropic case, you can think about the problem as one-dimensional. In an anisotropic case, you need at least 2 dimensions to describe. And for me, I think that the main challenge, or the main part that was missing in the previous work, is to remember that there are shear modes and slow modes in the system, and these interact strongly with the wave. So they're going to really affect the system, and we need to think about them. And another thing that was maybe hard for the weak wave turbulence description, so there were a lot of attempts of experiments and to measure the spectrum of internal gravity waves in the lab, and this is a very challenging, and one thing that is challenging there as well is try to separate them for slow mode. And one thing that I will talk about at the end is that in the lab, it's very hard to measure them. One reason is the separation from the slow modes, but it seems not to be a big challenge in the ocean. And we can ask ourselves why isn't it so hard in the ocean to measure a clear spectrum of weakly interacting internal gravity waves. So when we started working on this problem, I had a conversation with a famous oceanographer, which I will not tell his name, but what he told me is that, there are whales in the ocean, and I'm not sure that a nice Boussinesq equation can really describe what is happening in the ocean. So we were not trying to do that when we started to work on the problem. We were much more modest, and we said, okay, we just want to see what the 2D Boussinesq equation looks like and what it's going to give us. So if you want, there are two stages to solve the problem. Let me just look at the time. Okay. One is to find the right variables to write the kinetic equation, and so that you don't end up with a very complicated equation that you cannot analyze. And then we want to look for the turbulent solution. And to look for the turbulent solution, we really need to understand what are the universal boundary conditions that we expect in a non-isotropic system with a large set of shear modes, which are important for the problem. Okay, so what was done in 3D works in the past in the wave turbulence? So first they assumed the azimuthal symmetry, so it ended up to be two-dimensional. And then they took another approximation where they assumed that the horizontal scales are much smaller, are much longer than the vertical scales, and then this simplifies the equation a lot. And then they treated this part of the spectrum homogeneously. And what we're going, and they try to find a canonical Hamiltonian. Okay, and what we're going to do is slightly different. So we're going to use this non-canonical part. So by using that, I'm just saying that we're going to remember that we have another conservation law, and we're going to use that. We're going to use the non-canonical structure, and we're going to remember that the slow modes that are sitting here in the spectrum are very important for the type of solutions that we're going to look for. And we're not going to take a priori this assumption. We will see afterwards that our solution does give us concentration along the slow modes. But we're not going to take this approximation. Okay. So if you're going to use as a basis just your weight, then you're going to write your equations of motion in terms of the weight, you're going to get a very simple representation of the weights. So this is the linear part of the equation, V is the amplitude of the weight, and they interact in triads because it's nonlinearity of the order equation, so the nonlinearity is quadratic, and they have center V alpha beta gamma that describes the interaction of three waves alpha beta gamma, where alpha carries the wave number and the dispersion. It's not very important. The only thing that is a little bit important and interesting is that the wave basis is a good basis because it diagonalizes the energy and it diagonalizes the pseudo momentum. And then if you take these equations that I wrote here. So I'm going to do this derivation, which is, if you do a formal derivation, it's more or less straightforward for dispersive PDE. So I'm going to do that in the tutorial afternoon. So now you will just need to believe me that if you start on a torus, so that we'll take the boundary conditions to be periodic in X and Z. So that means that our Fourier modes are on a lattice with spacing L, where the box size is L. So when you are going to take carefully L to infinity, the interaction to 0, and look at long times, what you will get is a kinetic equation for the energy density, which has some similarities to the Boltzmann equation. And one important thing that you want to assume that will allow you to go to long time so that you see turbulence is that we're going to assume Gaussianity between the different modes. So if Z alpha is the amplitude of the wave alpha with wave number k, so I'm going to assume that the initial data at time 0 is they're uncorrelated. And E alpha is the average energy density because the alpha star is the energy density at wave number R. Yes.
E is some function of K,
Yes.
and what power of K is this?
So it's anisotropic. So it depends on the cosine of the different angles, on the sine of the different angles, and it also depends on the wave number amplitudes. And the dependence on the wave number amplitude is the power of the wave number amplitude. So if you want the homogeneity degree with respect to this variable is 1.
And it's not homogeneous, same homogeneity with all the variables.
No, just with respect to the absolute value of K, it's homogeneous.
Okay, so that's one.
Yes. Okay.
So I've got one question about the periodic boundary condition. So does that mean that what does that mean that you're assuming about the vertical density profile? Does that have to be periodic as well?
No, so my original the original certification was linear and not periodic. What I'm assuming is the deviation from the main profile is periodic.
Okay.
But if you want, it's not really a fundamental assumption. It's an assumption if you want to rigorously prove things about solutions of the kinetic equation, because I'm going to take L to infinity eventually. So if you want, it's a technical assumption too. There are terms that you need to estimate in the kinetic equation. So it's a technical assumption to estimate them, and also we don't want to include boundary conditions in the X and Y domain. Okay, and then because I don't have a lot of time, so I'll just say it quickly, because our base is diagonalized both the pseudo momentum and the energy, so that sets restrictions on the interaction coefficients. And if you think about the interaction coefficients as vector in 3 dimensions, because you have interaction inside, and you think about the constraints coming from the conservation of pseudo momentum or helicity or entropy, if it's more easier to helicity or entropy, and you include the restrictions coming from conservation of energy. So from doing really simple geometrical arguments in 3 dimensions, you will end up with this equation. So on the one important thing that I didn't say about the kinetic equation is that the kinetic equation is concentrated. So when you take time to infinity and L to infinity, all the interactions, the only interactions that will survive in the kinetic equation will be interactions on the resonant manifold. So in the kinetic equation, you have momentum conservation between the triad, and only the resonant interactions are important. So if you include all these descriptions, you will get that all this 3-dimensional tensor on the resonant manifold is actually completely symmetric, and it reduces it really simplifies the problem and makes the kinetic equation much more compact and nice. And I know that now you cannot really appreciate the simplification, but you can try to look for solutions of this equation with respect to this one. So this one is much more nicer. Okay, so we completed the first stage of the problem. We have a kinetic equation. It's nice. It's more or less simple, except for being non-isotropic. And now we want to find solutions. So first of all, there is a trivial solution, which is just when P alpha equal to 1, we call it the equilibrium solution, because it does not carry flux. I need to write the flux in order for you to understand why it carries no flux. But if you plug in here 1, what you get here is omega alpha plus omega beta plus omega gamma. And I remind you that we're on the resonant manifold. So you have this delta that multiplies that, so it makes the right-hand side 0, so it tells you that this is a steady solution. But we are understanding the turbulent steady solution, and the turbulent steady solution is a solution that carries flux. So one thing before we're going to look for our solutions, for a solution, F solutions, is that I remind you again the shear modes. So one thing that when I wrote the kinetic equation, I assumed that, so as long as I had my L in the system, I was always far away, some finite amount of distance from the shear modes. But when I took L to infinity, so I'm going to get closer and closer to the shear modes. And one assumption that I took that is going to break is the Gaussianity assumption. So this is no longer going to hold. So if you're going to consider this equation, one thing that I need to remember is that it's not holding. It should break down when I'll take omega alpha to 0 in my equation. And okay. So as I told you in the problem, nothing is isotropic. But if you look for symmetries of the coefficients in the kinetic equation, so they're not isotropic, but they're all symmetric with respect to dilation. So if you multiply all the wave vectors with the same scalar, it has an homogeneity degree, the interaction coefficient, and also omega is homogeneous of degree 0, it's just cosine of theta k. And then if you look for solutions which are also symmetric with respect to dilation, it fixes the separable form k to the power w times an angular function, where big K here is the amplitude of the wave number. So we're going to look for these separable solution, and if we're going to find one, it will tell us something fundamental about anisotropic systems, because if we find a separable solution, it tells us that an anisotropic, if it's going to be also universal for other systems. So it tells us that in an anisotropic system, the energy transfer is actually determined, if you want, on the sphere of radius 1. So this determines the anisotropic energy transfer. And then from here, it's happening in scale invariant way. with a particular, so if you want a part of this plot, so it will happen in a symmetric scale invariant way when W is the power law of this cascade. So yes.
Find one solution and still invariant. Why would it keep that problem is still invariant?
It does not mean that the problem is scale invariant. It's just that if I'm going to find, so there are two approaches. Either you find a solution and prove that it's unique. It's a unique solution that has a flux, or I would call it, as a physicist, I would say, okay, if I find a solution which has a flux, then you can now either believe that this is the turbulent solution if it satisfies all the things that you expect from turbulence, or you go and do a numerical simulation and see if it fits the data and fits your numerical simulation. Okay. So I'm not saying that the solution has to be scale invariant. I'm saying that I'm going to look for a solution which is not isotropic, but scale invariant in the absolute scale. And then it seems like you can have a family of solutions, because for each, so if my solution is KW and some function of the angle, which I can think about with some other power law that depends on theta. So now I'm looking at this part. So for each W, maybe I can find an FW that will make this thing a solution. So I will have a family of solutions that depends on my variable W. And at first I was worried that I will have a family of solutions and then what I'm going to do with this family of solutions. But if you're writing the flux. Okay, so I'm not going to write the flux now. Anyone is interested, I can do it in the afternoon. So if you write the boundary conditions for the flux, and you're asking which power law corresponds to a constant flux, it will actually determine a unique solution. And it will tell you that there is only one solution that has constant flux. And it gives you a unique power law, and the unique power law, just like in the isotropic turbulence case, is determined by the homogeneity degree of the interaction coefficient and the dimension. And in our case, it gives us -3 here. So here I was relieved that at least from the flux, I can determine a unique power law. And this is the only power law that gives me a constant flux and gives me a solution that can correspond to turbulence. And then if I have this part now fixed, I want to look for the angular part. And now if I'm going to look for the angular part, so I'm going to remember that the shear modes are going to play an important role and I need to think about them. So I'm not gonna, so there are some considerations that you need to take with the pseudo momentum, but we're not gonna talk about them now. And if you're analyzing the solution, so you will get that you have a candidate for varying that W, you will have here a candidate for FW being constant, and it's just a line that depends on W. And if you plug in the specific W that we get as a candidate for turbulence, then you will get an ansatz, you will get a value for F of W, which needs to be -2 from this very simple analysis. And then if you go and plug it in the solution, in the kinetic equation, you'll get that it's diverging, the collision integral. And But then if you take a closer look at this divergence, what you actually see is that it changes signs from plus infinity to minus infinity in a very special, around a very special line, and this is the line where kx is equal to 0. So if you want this integral to be finite, it's asking you for a regularization around the shear mode. So it tells you that this is a solution if you regularize around the shear modes. So what we did is we introduced a regulator around the shear modes, and when we took this regulator to 0, then we get a finite solution that does not depend. So we took this small part of the angle sector of width delta, and what we got is that energy density when delta is going to 0 is this energy density. So if this is the solution, it tells us, as I told you, that the if you want the anisotropic part of the system, you can determine it on a circle of radius 1, and then from here it's proceeding in a scalar invariant way, and here the angular part of the caves is cosine theta k minus 2. And this is how it looks. And we were very happy with this result. And then when so back to the whales, when we were writing the paper, so Oliver said, oh, we actually need to compare it to the Garrett-Monk spectrum and see what we have to say about the Garrett-Monk spectrum. So the variables that we work in are kx and kd. If you change the variables to d, k, d, d omega, so what you get is exactly the Garrett-Monk spectrum, which is nice, and it was the first time that the two-dimensional Garrett-Monk was derived from first principles. And another nice small things that you can learn from the analytical from this analytical solution is, for example, so if I remind you one small thing about data of internal gravity waves, so I told you that the data is always separable in kz and omega in the measurements. So if you return to our family of solutions here, where you have W and equal W, so actually the pair, this power law minus 3 is the only power law that makes this the spectrum in the kz d omega power law separable in kz and omega. So this is one mathematical insight about the separability of the equation. If you want if you're in the turbulent regime is what makes you separable in kz and omega variables. And to finish my talk, you can ask yourself what is the message of this diverging collision integral around the shear modes. So one straightforward message is that the shear modes are important, or the slow modes are important. So if you want to solve the full problem, you need to include them, and then the effective degrees of freedom are not waves, they're something else. So maybe we can do some renormalization, first order renormalization, and include some, in a way, the shear modes in making the waves different degrees of freedom. But another simple message, and this is related, so in the ocean there are no regulators and there is no problem of measuring a clear spectrum of internal gravity waves. And I think that the reason for that is that you have rotation in the ocean. So the rotation is small compared to stratification, but analytically it's very important because it lifts the degeneracy of the connection that you have from waves in the degrees of freedom from when omega is going to 0. So if you don't have rotation, when omega is going to 0, you're continuously to the slow modes. But if you introduce also rotation, so omega k never going to 0, because when you are approaching kx equal to 0, the omega k is f. So if you want, you have always a bound which depends on f from the slow modes. And then when we realize that there is actually a physical regulator in the ocean, so we added rotation to our problem, and then you need to go to 3 dimensions because otherwise it's trivial. So if you go to 3 dimensions, achieve the symmetry of one of the horizontals, where you still work on a vertical side. So everything is a little bit more complicated, but this power laws of -3 remains -3, and what is going to change is the way the angular part behaves. But once we have a physical regulator, so one thing that we checked is that when we take f over n to 0 in the 3-dimensional with rotation problem, so we reproduce this result, so we get the result we obtained in 2 dimensions when f is going to 0, and then we did a numerical simulation of the 2D Boussinesq equation with Pansana bar to see if we see the spectrum. And weak wave turbulence, this is the spectrum that we see. So we see that the spectrum is behaving like this spectrum. So what you see here, when you're not very, very close to shear mode, so the black ones are shear modes. This is the solution of this is the inertial range when it's normalized to the theoretical prediction. And when f is not 0, so now we're working on the problem when f is small, but not infinitesimally small. And the problem is interesting, and it seems much more complicated, and we cannot do simple perturbation theory because the limit when f is going to 0 is so singular. And then we have other fundamental questions that we ask ourselves. For example, we ask ourselves if this singularity that we see in the ocean around inertial modes, is this really a true singularity that you get in the equations, or is it actually just a coordinate singularity that depends on the variables that you measure, or it's a singularity that is coming from the boundary conditions that you have in the ocean? And we expect some interesting insights when I hope that we will have results in the next few months, and when f is not 0. Okay, thank you for listening.